So we have talked about quantum computing applications in industry, but it's not only industry and not only businesses that can benefit or should benefit from quantum computing. And I'm very glad to have here Wadim here from Bundesdruckerei, and they are currently having a project on exploring the possibilities of quantum computing right here in federal government. And he will share what they have found so far. Welcome, Wadim, please.
Hello, everyone. So, Natalia, thanks a lot for the nice introduction. I would like to say a little bit more. So, who am I? I'm a theoretical physicist. I did my PhD a couple of years ago. I dealt with black holes, I dealt with particles, and then, well, I left academia. And afterwards, I dealt with AI for a couple of years, and now I'm back in the quantum world as a quantum physicist in this wonderful project, HUGO, which I will be telling you a lot more about. But before I do so, I would like to spend a little bit of time to talk about the Bundesdruckerei itself. So who are we? We are a technology company, and we are a very historical technology company, and we stand for security and sovereignty. We are 100% federally owned, and we have a very special position to develop secure products. You all have Bundesdruckerei in your pockets, be it IDs, be it passports, be it driver's licenses, or even the money. This is all Bundesdruckerei. But security goes further than now. Security is also a topic of the future. So naturally, Bundesdruckerei has an innovation department where we assess the risks and benefits of upcoming revolutionary technology. And well, quantum is one of them. And as a sovereign entity, as a trusted partner, it was natural that the federal administrations started a project with us. So let me give you a little bit more of background, not the Bundesdruckerei, but the whole quantum ecosystem. So the federal government has decided a couple of years ago that quantum is of utmost strategic importance. So here you can see a quote from the Bundesdatenstrategie. I also encourage you to have a look at the Handlungskonzept Quantentechnologie, but the message is clear. It's very important for the future. It's very important for us. So what do? We invest 2.3 billion euros into the advances of quantum technology and surrounding quantum technologies, applications into research and industry. And to our knowledge, there are more than 500 initiatives right now. Here you can see a map of all the initiatives that are known to this project at the moment. So this is an ongoing project, and I think it runs until 2027, and there will be a lot happening on this map. But what should be visible is there's a huge net, there's a lot of interactions, and it's a highly dynamical ecosystem. So with that, there are certain challenges that emerge. First of all, the federal administration would like to utilize all these initiatives. This is a very challenging task. The second thing, it's bridging the gaps. So what's the problem here? So quantum is a very, very old thing. So it's almost 100 years old, and it's academic in nature, and even worse than academic, it's physics, right? So it's a topic that no one really wants to deal with. It's a very, very hard subject. But you have to be a little bit of a physicist to be able to utilize this 100 years of experience, of results, of technologies, of ideas. Otherwise, they are lost into a physics language that no one really wants to read. And the third challenge is that quantum is not only supposed to be on the outside in society, in industry, in academia, but it's also supposed to be inside the federal administration. So the path to walk towards quantum integration into society, it should be a path taken by all actors, not only a few of them. Okay, so this is the situation. Let me introduce you. Project HUGO is an answer to these challenges. So we have the following structures. So we are partnering with the Federal Ministry of Finance. The Federal Ministry of Finance is also 100% shareholder of the Bundesdruckerei. So it's very much natural that this happens. And in our projects, we have three complexes. So we focus on security. So here we kind of assess the risks and benefits of quantum technology, also quantum computing. And analytics, so here we are trying everything that is known. So all the quantum advantages that are there, we assess them, and we develop new algorithms, and we try to understand what's quantum machine learning really about. And at the end of the day, we also want to integrate everything. So to develop something quantum, it has to be useful. It not has only to solve something, it has to be integrated into something. So you cannot have those two things without this thing. So here we all very much care about bringing everything together to form something which is truly quantum, truly a quantum application. And for us, we not only focus on applications, we focus on sovereign applications, since we are trying to do this for the federal administration. So this is our setup. So developing applications is a little bit special if you do this for the federal administration, because there are certain requirements that you have to satisfy always. So there are regulations. There's a topic I could talk for 2 hours straight on this point without even preparing. And it's all about, well, for example, for example, data regulations or export control. There's a ton more things, but they are important. They are there for a reason. And we have to satisfy them. We have to take them into consideration. Federal applications, they're usually very, very complex, to say the least, because usually you don't have isolated incidents, you don't have isolated systems, everything is kind of interconnected. And you have to treat it as something interconnected. And for that, the current way quantum is applied is not enough to these highly complex problems. And also the use cases are usually have a non-profit character, so progress over profit. And our mission to solve this, to develop applications under always not forgetting about the requirements, is that we want to enable a sovereign use in the federal administrations of quantum technology, but even more than that, we want to develop a sovereign use of quantum theory, if you want, and we want to go beyond solutions. So solving something is not enough from our point of view. We have to keep track, we have to adapt it, we have to keep it useful, not only make it useful. And also we want to establish something which is called quantum innovation thinking. Let me talk about it on the next slide. So here you see our portfolio. We are 10 experts, we have full stack capabilities, we are co-working with ministries, we stimulate academia and industry, we establish partner networks. I encourage you to look up Bundesquantenallianz. And also this is something we are very proud of. We use our quantum hardware ourselves. So we are trying to be really the experts who understand every little bit of quantum. So let me invite you to experience a little bit what we call quantum innovation thinking. And for that, I would like to tell you a little bit of a story first. So we all know Shor's algorithm. It promises us, hey, we will make anything secure insecure because we can crack everything, every password in mere seconds. Which is of course a threat, but what usually, this is also known as typically as the quantum advantage, but what is less appreciated is that this is far from being able to execute. So Shor's algorithm, it requires a lot of logical qubits. This is just not there. Never forget, currently we are in the NISQ era of quantum computing, so noisy hardware, and all the algorithms that are promised to us by looking at the algorithmic part, at the mathematical part, they require much, much more that is technologically available. So what do we do? So are we chasing this part? Are we waiting for the technology to evolve? From our point of view, we should also consider different things. So here, quantum innovation thinking is the idea to not only look at the advantage in terms of speed-ups, but the advantages that are given to us by having quantum. So what happens if we allow quantum, if we relax certain conditions of causality and nature to allow for a bigger picture, to be able to take a bigger stance and look at problems in a different way? And this is the quantum part that we would like to enable, that we would like to access, that we would like to use. And this is much more than just the complexity, the advantages. It is more about understanding. This is utilizing 100 years of evolution in quantum theory. So how do we do this? Let me show you an example of that. So we are focusing, never forget, on the unique quantum properties of a system. So how can we get the most out of it? So what do we do? Let's make a little bit of an example. So something which is highly routine in classical machine learning. So let's just take those dots. They are red dots, they are green dots, and just separate them. The task is find the perfect line that separates both of them. This is just routine thing to do. Okay? So this is very hard here. It seems impossible. So another trick, a highly routine thing to do in machine learning is just to apply a kernel trick, right? And in essence, what it does, it changes the perspective on the data. So we just move it around the data, we look at it from below, we scale it up, we do a lot of things to it, and in the end of the day, if we are lucky, this happens. So those data is now perfectly separated, and we know the perfect line, we solve the problem, everything's fine, okay? So this is called kernel training, and in the quantum world, a kernel can look like this. This is something we developed at Bundesdruckerei, and the idea behind it is to understand that these kernel trainings in classical machine learning, you kind of never know. You have to give the machine, you have to give the computer the perspective, and then the computer decides whether this is a good perspective or not. This perspective, this kernel, is a hyperparameter, it's called. But in quantum machine learning, this thing can be learned. It can also be learned in classical, please don't get me wrong, but there are certain nuances here and caveats here. But for quantum, it's highly natural to learn this perspective. I give the machine my data, and this data is then took into this quantum computer, and the quantum machine kind of looks for its own perfect perspective to solve this issue. And thereby, we increase explainability, because usually, applying such a perspective, we don't really get any knowledge about how we got there into this perspective. But in quantum, we can look at it. We know how the quantum machine got there, and we increase our understanding of the black box, right? So this is something that quantum offers us naturally. So this is the advantage, if you want, a new way to look at advantage of the quantum theory applications. So another issue emerges. You have to be very sensible about this thing. So you cannot just evaluate this quantum machine learning applications the way you would evaluate machine learning applications. If you look at things like accuracy or recall or whatever, these things will be awful on a quantum computer. Because remember, we're still in the NISQ era. The hardware is not very far evolved. We are not going to be able to feed the algorithm a lot of data because the machines cannot handle it, right? So we will have very bad results. So the solution here is, do not look at the known things. Look at the quantum things, things that are happening on the quantum computer, and evaluate the algorithms based on this information. And one thing that we can do, we can look at the learning, whether this quantum machine learning application learns. So this is called a loss function. Shortly speaking, if it goes down, very good. If it stays down, even better. But the problem is, we have here two ways of computing. We have to give the machine the strategy to learn. But do we give it a stable strategy or a fast strategy? It's very important to have this assessment, because if you want to run it on a real quantum computer, you can only get this far. It's very tough to learn. So we decided to do stable computation. We put it in this kernel, we put in the data, and we got this thing. It doesn't look like much. It's two curves, one is blue, one is orange. But the point is, both of them go down. Okay, this is learning. This orange thing is really on an ion trap quantum computer. Something has been learned. This is what we want to know, whether this is able to learn in the quantum world. If you do not appreciate these pictures, I encourage you to also change your perspective like this kernel, and just appreciate that here something has learned in the quantum realm, on a quantum device. It happened. We learned something, right? Okay, so let me show you also some other projects that we are currently running. So we have very theoretical projects. We have very practical projects. Practical, please do not misunderstand. We do not have a quantum internet as a hardware, but we are dealing with this project, and for us, it's a practical project. So I would love to talk to you about all of them. But this will take like 4 hours, at least. If I'm really in a good mood, it will take weeks. But let me highlight some of the results that we are seeing. For example, optimal control. We heard already from Heike that there is something called error mitigation, and here you can see it in action. This is the same calculation that you saw before on this ion trap device. But if you go to superconducting, you don't see any learning anymore. And this is a technological aspect. They behave very much differently, those superconducting qubits, than ion traps. In superconducting, you have to make the step to tame them. You have to apply control theory. And only then can you really work with those superconducting qubits. A lot of these things are being automated right now. It's a great thing. But superconducting, you have to have a different mindset. You have different skills to really get the most of it. And these optimization, these control methods, they automatically lead you to the understanding of noise in the quantum system. And if you understand the noise, you can control the noise. And from that, you can do a lot of things. You can characterize, you can evaluate the hardware, you can do many, many different nice things. So another really interesting project is this quantum cyber security. I think every one of you has heard about QKD. There are protocols, they are secure, but the protocols are secure, but after the protocols, there has to be a post-processing step. And this post-processing step is kind of corrects all possible errors and everything, and then you have the privacy amplification, because you cannot be 100% secure in this step. But what we might imagine is to ask ourselves, how much of this post-processing are we maybe able to put into the protocol itself? And asking these questions automatically introduces the question, what is the role of quantum computers in a QKD protocol? This is something we try to answer, we are working hard on it, and well, due to time reasons, let me talk to you also about something very theoretical what we do. So if you are working in the quantum realm, at some point you have to become real, classical, in order to interact with us. But the question is when? And what is the physical nature of this quantum information? How do we know whether we get the most out of it? And how do we know whether maybe we get only like the irrelevant part, or at least we want to have the irrelevant part, not the most of it. But nonetheless, these questions are very important to us, to understand really the quantum theory, to utilize it, and to make it work for us in all of its glory and aspects. So let me summarize. So what you saw is there is a great interest for the Federal Administration to utilize quantum technologies and quantum applications. They are not only scientific tasks which you can solve, they are things that have meaning. You have to look at them at a broad context. Quantum innovation thinking, we unlock the notion, a new notion of quantum advantage. What was before the speed up, the quantum advantage in terms of complexity, now becomes the answer to the question, how far or where can I go using quantum theory? So in short, what we do is we walk the road to something which we call applied quantum theory. Something which if you're a student of physics, you should never utter those words in your class, okay? It doesn't make sense, but still, it kind of does make sense. And we try to formulate the sense. So the only thing that remains to say is, thanks a lot for listening. Yeah.
Thank you very much, Wadim, for this exciting contribution. Are there questions now from the audience right away? Yeah, here comes the microphone.
That's a very fascinating, really, a very good summary also, and looks like the Bundesdruckerei kind of managed to grab the interesting parts of this. Can you give us some background on how came this about? Because for me, let's say the first thing to think about would not be Bundesdruckerei. Let's say 10 years ago, who gets this topic? How did you manage that? Does it come from cybersecurity, or where was the decision making?
Well, we take innovation very, very seriously. And cybersecurity is, of course, definitely an argument with which you can convince a lot of movement. But quantum, since we are really looking at finer details, is much more than just security. It's kind of all around it, what makes quantum security. And we were able to convince that this is important. This is the short story, but I'm afraid I need maybe 2 hours to explain the whole picture. But great question, actually. Yeah, it's not normal what happened.
Yeah, we have one more question on the other side, maybe. Can you? Thank you, Nina.
very much. Thank you for the presentation. I have only one short question. Do you have some concrete application in the future in your program? Because the theory is very fine, but it will be great to see something concrete.
Oh, yeah. So what I actually didn't talk to you about are concrete examples of this sovereign applications that we are developing. What do I say now? Most of them I cannot even talk about, I'm afraid. But we are very much interested in generative approaches to data. So something like data synthesis is very important to us, or big graphical networks that you want to kind of optimize in their setup, like in their combinatorics, or where you can define new metrics that you can optimize, but not annealing. Please do not misunderstand me. So these are very important things that find applications in these federal administration use cases. But like I said, these things are vast. So you cannot just isolate some concrete thing in these applications. You have to consider the big picture. And I'm afraid I don't have the time to tell the full story here. But very great question. Maybe we can talk in private afterwards. For a second.
Thank you very much. I would encourage you now to speak to Wadim in our networking area, and he will be glad to answer your question, even if they last for 2 hours, right? Thank you very much. And yes, a round of applause.